everybody to session 4 of the Disruptive Technologies and Emerging Technologies. Arthur, do we have a sponsor for this session? No sponsor, so thanks. So it was mentioned earlier today in one of the presentations by that mining has changed a lot. And from my perspective, new technologies have been gathering a lot of momentum over the last 5 to 10 years. Things have just started to change, but in my opinion, the next 5 to 10 years is going to be very exciting. Many of the new technologies have been well tested and accepted in the mining environment already. It seems that there is a clearer understanding of the opportunities presented by these new technologies. However, challenges remain on how best to implement them and finding the right balance for your operation. Efforts are still needed to continue to train a skilled workforce to meet the demands of these technologies. And on that note, I'd like to present the first presenter, Richard. I'll let you take it from there, Richard.
Okay, thank you very much. Okay, my name is Richard again, and I'm from the Helmholtz Institute Freiberg for Resource Technology. And today I will talk to you about our recognition of what are the main barriers to exploration these days in Central Europe, but maybe you can apply that to some other parts of Europe and the world. Okay, so if you look at what people think about different industries, it gets quite clear that the mining industry has a huge problem of image. So if you look at that here, so it goes from the top. Here where you have food production and retail and market, and at the bottom what you will find is the appreciation of mining. So mining industry has a very, very bad image. I don't need to explain that to you. The only thing is that we have to accept that as a fact. We cannot change people's mind that easily as maybe it's not what we try to do. The other thing is that if you want to operate exploration or mining, and I guess I don't have to explain that to you, you have to gain credibility and trust. And for that, we need to build trust. So as a exploration company or as a mining company. And that is something that is quite difficult to do and to apprehend. Okay, so the other thing which is extremely important right now is if you talk to politicians and to local communities, they will tell you that we don't need exploration, we don't need mining, because we will go towards circular economy. And if you believe that, then everything will be recycled and there is no need for the influx of new material. Everything will be recycled. What people forget is that that is not possible. So the laws of thermodynamics refute that, but on top of that, you have another aspect that we want. There is the new generation of green energy, and this green energy is extremely demanding in typical complicated raw materials. So that's the reason why that we are confronted to a fact that everyone needs raw materials, but no one wants to have exploration and mining. So what is the answer? And we think that the answer is innovation. And we try to find a solution. So in part of the initiative from the EIT raw materials, we try to discuss about that and try to find out what is reasonable, what should we do in the future. And here what we need is, we need to sustain or at least go towards this circular economy. We need to boost European competitiveness. And for that, we need to have a so-called sustainable mining and sustainable exploration, which is quite difficult to attain. So, what we came up with is an idea where we want to test that. So, in order to test that, we need reference sites. So, what we will do is in the next few years, within a project funded by the EU, is to set up 3 reference sites in Europe, where we will test both new technologies, but also the reaction of stakeholders to this new technology to find out what is acceptable and what is not. And so, thanks to the EU, we have quite a big budget to do so. So what are the project objectives? So the first thing is we need to engage society. We need to find out what do they want, what do people want, what do the stakeholders want, what do we want, and at the end try to find a way to invigorate exploration. So, and for that, as I said, what we want to know is what is the impact of innovation, what people are thinking about new technologies that will be less invasive. Okay, so how we do that? As I said, we want to have 3 reference sites in Europe, one in the north of Europe, in the Arctic, a very sensitive region, one in Central Europe, where you had a history of mining, but after the reunification of Germany, it stopped, and one in Spain, where there is 5,000 years of history of mining. And what we want to do is to have an innovative approach and try to engage stakeholders at an early stage of exploration. Even before we start exploration, try to find out how we can bring the stakeholders along so that they have an impact on the way how we do exploration. So it has started a few months ago, and we have a lot of discussion with stakeholders right now. So at the end of the day, what we want to do is increase the so-called license to operate, which is a term that I don't really like because it means that you have a piece of paper and you can do whatever you want, which is not the case. But what we want to do is increase the acceptance of exploration. And we want to analyze with quantitative ways what is the impact of exploration and mining on stakeholders. So as I said, we were lucky to find 3 reference sites that are extremely interesting. One is Sakatti in Finland, maybe you have heard about it. It's an exploration site owned by Anglo American, and Anglo American is a partner of this project. We have a test site in Gaia, in the Ore Mountains, or Erzgebirge in Germany, where there was a long tradition of mining, but as I said, after the reunification that was forgotten, and the new generation of citizens is very against mining. And you have Rio Tinto and Las Cruces in Spain, where the acceptance is extremely high. So Rio Tinto in Spain, a very huge site, the biggest open pit mine in Europe so far. They are expanding, and we will try to find out with them if we can find new technologies that can help them to explore, at the same time to increase the acceptance. The other one is Las Cruces, very near to Sevilla. Very important site because it's very near to the city. So people in Sevilla know exactly what's going on in Las Cruces. And right now there are some troubles on this area, so exploration is a little bit difficult in this prospect. Okay. Gaia, as I said, very important for us because long tradition of mining that stopped after the reunification. And right now you see all this forest. Sorry, let me finalize that. Sorry. Okay. So all these forests are natural reserves now, and the acceptance for exploration and mining is extremely low by the population. And the last site, which is even more complicated because it's Arctic region, it's at the boundary to local communities that are difficult to deal with, and this site is on a nature reserve as well. So it's an extremely complicated site, but we are happy to deal with that because in this case we can also both look at non-invasive technologies but also try to find out what is the impact on stakeholders. So the partners we are working with are a straight over technical and more sociological aspect, but also with industry partners, and that is extremely important. We have industry partners, and they are working with us. So industry partners both in the exploration, but also in the mining industry. So what do we want to do? So we want to restrict our approach to non-invasive technologies. So it means that we will not go to the ground, or we will limit our access to the ground to the minimum, and we will try to use geophysical data, remote sensing data to see if the acceptance of the population and stakeholders is increased. So here what you see is one of our helicopter with an antenna, so you have on top here's the source, and then the reception is below, so it's 36 meters, and you can sound what is underground. So we need now to convince both the industry and the stakeholders that this is a viable alternative to other technologies that are more invasive. Another technique that has been developed recently is the full tensor magnetic radiometry. And in this case, we will get the full tensor of the magnetic field, and that also a recent development that will help us to identify possible ore bodies on the ground. Sorry. So altogether, so we are working with partners developing these technologies. So as I said, we will have magnetic, electromagnetic, with passive source or active source. And we are developing this technology conjointly, and we will try to find out, can we find some references that are that we can validate, and the idea is that we can certify these technologies in terms of technology, but also in terms of acceptance. So at the end, what we want is to have these 3 reference sites where exploration companies can come, or developers can come and test their methods in the future. So, and at the end, what we also want, if it works, I hope, is also develop new technologies based on UAVs. So I hope it works, and you will see that the movie that we drew recently. So what we are doing is we use UAVs to go beyond what a human being would see, and on top of these UAVs, it's not only take pictures, but what we want is to have sensors on these UAVs that are helping the geologists. So it flies on different conditions. So you see here in the snow, there was a snowstorm. We have a hyperspectral camera, we have a magnetometer, we have a LiDAR on these UAVs, and we are able to map quite accurately the areas. What we get at the end is that what you see here, so we have a 3D model of the Earth surface, and on top of that we have indication of geophysical data or remote sensing data. So what I wanted to say, and that's probably my last word on that, is that it is very important to reduce our footprint on Earth in order to get people along. The only way we will be able to do that in Europe is to talk to people and make sure that our technologies, the technologies we will use in the field, are accepted. Thank you very much. And I think Arthur will be happy because I kept it very short.
Yeah, shorter than I expected. Thanks very much, Richard. Okay. Did you want some questions?
I don't know. No, if there's no questions, there is no questions.
I don't think we're doing any questions.
Okay, no problem.
That was just for the last session. To present the next speaker, we've got Dr. Chris Broadbent from Wardell Armstrong, and he's presenting pilot-scale testing of the flotation and chemical processing of lepidolite concentrates from a magnetite project in Portugal.
Yes, thank you very much indeed, and good afternoon, ladies and gentlemen. It's getting a little bit warm in here, so hopefully we'll rapidly go through this. Lepidolite concentrates are, of course, one of the hard rock minerals which contain lithium, and lithium is very much in the news, very much a wanted element at the moment because of the electrification of vehicles. And really, if Europe is to produce any significant quantities of lithium, it's going to be by hard rock mineral processing as opposed to brines, and lithium from brines in South America is by far the lion's share of lithium production. But in Europe, we're left with lithium in hard rock minerals. So this is some of the results of one of the Horizon 2020 projects that we heard about this morning. FAME, Flexible and Mobile Economic Mineral Processing. Part of the FAME project is looking at the processing of lithium ores. FAME looks at a number of different types of ore, including the pegmatites, and of course the pegmatites are quite a source of these lithium minerals, especially lepidolite, which is one of the lithium micas. I've already alluded to why is this important. The demand for lithium is growing exponentially, and it's growing exponentially because of one factor, and that's the electrification of vehicles. The use of lithium-ion batteries in those electric vehicles generates a significant demand for lithium, also other metals such as cobalt, nickel, graphite, copper, but you know, it's not called a lithium-ion battery for no reason. Lithium is the lightest metal. If we're talking about the electrification of vehicles, we're really over the next 10 years talking about the development of lithium-ion batteries, and that's going to require that assessment there shows an over a 4 times increase between 2017 and 2027. I think that's probably on the low side. We're probably looking at a somewhere between 5 and 10-fold increase over the next 5 to 8 years. FAME, as I've already mentioned, that it's flexible and mobile economic processing. It's one of the Horizon 2020 projects. It's commenced on the 1st of January 2015. It finishes 31st of December this year. 16 partners, 7 different countries represented in the consortium, and it's a total research budget of 7.4 million euros. So significant amounts of research funding from these EU research and innovation projects. Just where Gonçalo is, it's to the southeast of Porto, or if you prefer to the to the southeast of Porto, or to the northeast of Lisbon. Situated in granites, and there's a number of these distinct pegmatite ore bodies. Mineralogical characterization of the Gonçalo pegmatite is dominated by the lithium mica, lepidolite, but also significant quantities of another lithium-bearing mineral, amblygonite. And I'm indebted here, I think this work was done at one of our partners in FAME at Camborne School of Mines, but also the Natural History Museum in London has been responsible for doing the mineralogical characterisation of these ores. Just a note of caution, lithium is a difficult element to analyse for. I think you should treat all lithium analyses that you see from historical sources with a degree of scepticism and a degree of caution. There's probably plus or minus 10% difference between any one set of data. And just look at that graph there, there's over 10, depending on the technique you use to analyse for lithium, there's well over 10% difference between the techniques. So you do need to know about the technique that's been used to generate the data, and you do need to know exactly when that data was collected. There's a very good paper that Robin Armstrong of the Natural History Museum presented at a lithium conference a couple of months ago at the Geological Society of London, the challenge of lithium determination in minerals, and I recommend anybody with an interest in lithium to have a look at that presentation. It's easily downloadable on the GeolSoc website, but it really does highlight some of the potential errors. What we're talking about here, and here I'm indebted to the partner of FAME LNEG, the Geological Survey of Portugal. They've been carrying out some pilot plant test work, a very basic flow sheet, desliming operation, followed by flotation, then followed by flotation of the tails from that flotation to recover other byproducts. This is to upgrade the lithium from a concentration of about 1.2% in the original ore up to lepidolite has, you should be able to get up to 6.5% lithium oxide in a lepidolite concentrate. We've been successful to get up to about 5%, 5.5%, and 6.5 would be stoichiometric lepidolite. I just want to show you a video of these pilot trials that have been taking place in LNEG's pilot lab in Porto. We've been processing at semi-industrial scale up to a few hundred kilograms an hour processing. Very successful results. We've got another campaign scheduled for the next 2 weeks where we hope also to recover byproducts from the original tailings from the lepidolite flotation and to sort out some of the problems with the lepidolite froth. Also, very importantly, we're recovering the heavy minerals that are in there as well. That's cassiterite that's present in the Gonzalo pegmatite, and the technology allows you to take out that cassiterite as a byproduct as well before the flotation. Slimes removal, very, very important. You do lose some of the lithium content, but of course with any flotation process you're restricted to a minimum particle size for effective flotation. The flotation, there are no bespoke flotation reagents for these lithium minerals. Flotation of lithium micas, as far as I'm aware, hasn't been carried out on an industrial scale anywhere in the world. The Australian hard rock production is virtually exclusively from spodumene. Certainly, if we could develop this process to enable lepidolite flotation as a pre-concentration step, I think that's going to be a first, certainly a first for Europe, but I think it's a first for the world as well. The flotation process, the classic flotation, having problems with the froth stability and overproduction of froth, that should be sorted out in the next set of pilot scales. Solid waste disposal there, we're hoping with our process and then taking the tailings from the lepidolite concentration and recovering the feldspar and quartz for the ceramic industry. We hope that the solid waste generation will be less than 5% of the original ore. So we're not quite a zero waste process, but it's getting on for a zero waste process. So these are some initial results. We're able to get, there it says 4.7% lithium oxide concentrate, with probably just the last tests were probably up around 5%. We're now starting the feldspar product, K-feldspar and plagioclase feldspar. We hope to be able to recover 75% of the feldspar. Importantly for the ceramic industry, it will have a lithium content, and although that lithium is reported as a lithium reduction in our recovery, the ceramic industry likes small percentages of lithium, so it's not really gone to waste. And of course, the work we need to look at the geometry of the flotation cells. They weren't totally effective during that pilot plant test. We think we know how to improve that. We will produce the heavy mineral byproduct, and certainly we've got every expectation of a highly saleable cassiterite product. But of course the flotation concentrate is only half the story. That takes you up to 5–6% lithium. You want a 29–30% lithium feedstock for the battery manufacturer, and then that's chemical processing. And here one of our colleagues in Freiburg in Germany, Geos, has been doing the chemical processing. We've been looking at a roast leach operation, getting very good leach recoveries of lithium, 96–97%. At temperatures there, it says 850 degrees. We've been able to reduce that down to about 750. You need that temperature. It's a very intense chemical process. Oh, sorry. And we've been able to then convert the lepidolite concentrate into a more meaningful product, and that can be one of the lithium salts, and eventually what we're wanting to create is a lithium carbonate precipitate. Lithium carbonate is one of the main feeds for the battery industry. There is an argument at the moment that we should be looking at lithium hydroxide production as well. And again, what we're looking at in the next phase of what we're investigating will be production of lithium hydroxide instead of carbonate. But we can have a very effective production there of lithium carbonate. That powder down at the bottom there is probably the first lithium carbonate produced from a European lithium mica source. Hopefully that can be demonstrated to be a battery grade, and hopefully that can go a long way towards valorising these European hard rock lithium resources. So one of the other things that makes a lot of sense for the economics of the process is to recover any byproducts. In the case of Gonzalo, it's cassiterite and topaz. They can be recovered relatively easily. In some of the pegmatites we've looked at, niobium and tantalum are also present, and of course they're well worth recovering as well in the fine fraction. So conclusions, we hope that certainly by the end of the next couple of months worth of test work at Porto, that we'll have had successfully demonstrated lithium mica flotation at TRL6, which is slightly above what we promised in our project proposal. We didn't really think we were going to major in lithium production at all. It's one of those things which, as fame has developed and grown, the importance of lithium has developed and grown, and we've decided to put more emphasis on the lithium recovery. We do believe that Gonzalo has the potential to become a significant lithium source, and of course there are other similar type hard rock lithium deposits throughout Europe which certainly have the potential to give Europe some of the lithium production. At the moment, Europe produces less than 1% of the world lithium. If the demands of the auto industry in Europe are to be met for electric vehicles, I think strategically Europe will need to produce an awful lot more lithium from its own resources. Further test work is underway. That further test work will enable us to produce at least some first estimate OPEX calculations. At the moment it's looking at the total production costs through to lithium carbonate from these lepidolite deposits, looking at about $6,000 a tonne, which at the current price of lithium carbonate of $12,000 per tonne, of course, looks very attractive. However, that should be tempered against the brine production costs, which are probably in the $2,500 to $3,000 per tonne lithium carbonate. But there's a great advantage with these hard rock processes. They come into production and can come into production in roughly half the time it takes to develop and upscale a brine production. So if we're talking about lithium production in the next 5 years, Really, it's got to come from hard rock production rather than new brine deposits. So there is a role for hard rock production of lithium. There's certainly a role within Europe, and certainly the European motor industry, I believe, wishes to see a much greater diversification in sources of lithium and processing, first of all, to produce a lithium concentrate, and then further chemical processing to generate lithium carbonate is viable, economically viable from these European resources. So I'd just like to say thank you very much for your attention, and I wish I could give everybody a cold beer because it is somewhat hot in this room, but thank you very much indeed.
Thank you, Dr. Broadbent. Very interesting presentation there on something that I think we're all taking notice of all these days. Interesting projects in Europe too. The next presentation is Jane Shaw, who is a principal consultant with the ERM, and the topic of her presentation is water risk management, managing project and financial risks across the mine life cycle. Very much.
Good afternoon, Dobar dan. So yes, I'm going to talk about water risk management, and it sounds like from the presentations we've had so far that I'm kind of preaching to the converted, but nevertheless I'm going to go through to explain some of the ways that ERM is working to help clients to manage water risks, because you know, it's a material risk. We all know it. If we haven't had problems so far, we will have problems in the future. It happens at many stages throughout the life of a mine. We've got issues such as too little water, too much water, not the right type of water, and they can all be fixed by engineering solutions such as a pipeline, but they come at a cost. They're either a financial cost or a reputational cost or both. So leading back to the comments that my colleague Geraint was making earlier today, we help you to manage your water risk in order to create the mine we want to see. So challenges, needs and challenges. Mines are typically long-lived. They're often situated in areas where there's increasing competition for water resources. Water demand is rising globally, increases in per capita consumption, expansion of irrigated agriculture, industrial development, population growth, etc., etc. We can divide water challenges into questions of quantity, quality, discharge and stakeholder concerns. So when we're talking quantity, we're not just talking not enough, we can also be talking about too much. Floods, storms, spring melt, all of these things have the potential to create excess water, increasing the problems of effluent leakage, tailings dam failure, pit flooding, how to discharge, where are we going to discharge it, when can we discharge it. So there's many examples nearby of too much water, flooding mines, taking tailings material with them downstream as they flood them, so on and so forth. So alternatively is of course the dry weather. The UN reports that 2/3 of the world's population currently live in areas that experience water scarcity for at least 1 month a year. And the Carbon Disclosure Project in 2017 states that approximately 25% of mining production will be vulnerable to climate-related risks such as water shortages by 2030. We worked with one client who was unable to obtain their permitted water supply due to prolonged dry periods over 3 summers. In addition, when they were abstracting, because the flow was so low, the water was contaminated by fecal matter from discharges upstream, which meant that their process was compromised, and they were only able to operate at 60% capacity, and are now considering a $100 million water treatment plant to fix this problem, which simply wasn't recognised at feasibility stage. They took their license, they have a license to abstract water from a river, and they took that as a minimum. We're always going to be able to have that, but that's just not the case. So obviously a strain on water supply can lead to water quality issues, either by forcing companies to accept lower water quality, leaving better quality for potable supplies or the environment, or because the water is being used and it's being degraded upstream somehow, which means that water quality discharge standards are rising. Water quality is considered on a basin-wide case, and so other factors besides the projects can influence the water quality discharge requirements. We're working with other clients who are in accession countries, EU accession countries, who are trying to design their mine water treatment processes, so the location and how they treat their water to meet the Water Framework Directive and transboundary conditions, which, as you can imagine, are quite complex for a country that is not already within the EU. So, stakeholders, I don't need to tell you this because about 40% of you answered the question 2 this morning, that why do stakeholders object to new mine projects? Because of water supply and pollution. So it's a very sensitive issue. Between 2000 and 2017, water-related issues were implicated in 58% of mining cases lodged with the IFC's Compliance Officer Ombudsman. Try saying that out loud. And another example, community protests over water pollution concerns meant that one mining company has been unable to commence operations for 6 years. Revenue losses haven't been estimated, but lease costs and capex costs at an NPV of $100 million have been lost. In another example, in a recent presentation, Anglo American stated that they consider that regulatory or reputational damage to water issues has a potential to affect their EBITDA by 70%. In light of these challenges, mining companies must enhance their approach to water management, including considering it as a shared resource with other users within the catchment. So how do they do that? As I mentioned in my introduction, ERM has been working with clients to build probabilistic numerical tools which companies can use to understand where their operation sits in the basin-wide perspective and how current and future water-related issues can be managed or opportunities can be realised. We start with a census. First, we identify the catchment of interest. It has to be big enough to include all of the significant influences on the project, but we also consider, do we need to think about infrastructure that's outside of the catchment, so slurry pipelines, water supply pipelines, for etc. For so on. So then we identify what the water resources are in the catchment that we're looking at. We look at the current, can't make it work, sorry. We look at the current climate in the region. Does it have dry summers? Does it have wet winters? What is the periodicity of that? The figure down here, and I will just apologise for the quality of the figures there. Some of them are deliberately blurred, so you can't really see what's going on. They're just an indication. Can you see any historic trends? This is 40 years of river flow data from 2 rivers within the catchment of interest. And you can see there are some ups and downs, but generally we've got a downward trend. So is that happening in your catchment? And we look at groundwater resources, what groundwater resources are available, are there any seasonal or historic variations we need to take into account. So we've identified what is present in the catchment. Now, who's using it? Data comes from river basin management plans, that's what this indicates. Population trends, the current and population trends, are people going to be moving into urban environments, out of rural environments, and how's that going to change water supply and discharge? Changes in infrastructure, so is there, in a move away from fossil fuels, are we building more hydropower dams, and is that going to have an impact? Are there any sensitive ecosystems in the catchment that we need to be aware of? Do we want to have interviews with stakeholders? So once we've identified the difference between the available supplies and the demand, we can look at future sensitivities. So too little water, such as the example I mentioned earlier with a company that could only operate at 60% efficiency. Alternatively, we worked with another client at PFS stage who were proactively looking at their water supply, and they had the same issue where they had very dry, the condition I showed you there with dry summers and wet winters, and there wasn't enough water guaranteed every year for them to be extracting up to their limit in the dry season. So we worked with them to locate a reservoir dam and to also to negotiate with the Brazilian government to change their license conditions. So for the first time, we have they got a seasonally adjusted license, so they can extract more than their original license in the wet season and store it and not extract anything in the dry season, so that they leave enough water for the social and ecological requirements within the river, within the catchment. Too much water, flooding, obviously we can do flood modelling either under current conditions or under projected climate change conditions, we can do that sort of thing. We can do changes in quality, changes in expectations or regulations. All of these things, these are identified as potential sensitivities. And once we've identified those sensitivities, we design appropriate modelling or analysis to address those. And for instance, if your problem is a surface water abstraction problem, we can run a surface water catchment scale surface water model. We can integrate groundwater or surface water with it. We can look at the effects of climate change. So this is an interesting example. That figure at the end there, which you can't quite see, this is basically the difference, projected difference between current rainfall and future rainfall under climate change conditions. And you can see the average annual there, there's no change. There's projected to be no change to average annual, but you're going to get a lot more water in the winter and a lot less water in the summer. So, and it's also slightly moved later in the year. So how are you going to have to change your water management, water storage conditions accordingly? And dewatering, flooding, groundwater assessments, groundwater supply assessments, and so on and so forth. Which leads to synthesising all of that into a catchment water balance. So the catchment water balance includes the mine water balance. And you can see in the grey box here, that's the mine water balance. The miners spend a lot of time and energy making sure all of the little details are correct, and they do a lot of monitoring. This is reported on monthly, up to corporate, it's very important. But there are a couple of lines here, the inflow and the outflow, and a couple of other sort of dotted lines, maybe supply here. And they're taken as fixed, and yet you can see that there are a whole bunch of other things that are influencing those figures that the mine doesn't have direct control over. So we look at those things and we put them into a dashboard. This is the site dashboard. The site dashboard is designed to track metrics which are critical to the site. And so we can be talking about real-time monitoring of river flow at the abstraction point or upstream of the abstraction point, or both. We can be talking about water quality monitoring points and the data from them. We can be talking about discharge quality, all these sorts of things. We link it to the live data, so you can see trends, and you see it's also it's map-based and it's interactive, so you can either use it, it's very much easier to visually see trends that are happening in water management before they become an issue, before they become an expensive issue. Also, these things are simple to understand for stakeholders. If you wanted to show those to stakeholders, allow stakeholders access to it, and they can go in and they can see for themselves what's going on. And then if you need to, you can link it to models and scenarios and revise them. So what are the problems that are happening? So the problems that we identified originally, they may change as time goes on, and these dashboards and the catchment water balance is flexible enough to add in additional information. So running scenarios, looking at groundwater flooding, do we need to increase the dewatering, and what effect is that going to have on the springs and other supplies around the mine? So if you are a large company with multiple operations, you might want to have a corporate dashboard which tracks different metrics that are important for the corporation as a whole. So you have each of your sites is here, you can zoom in to each one and have site-based metrics, or you have a look at the whole global portfolio. So as I said, it's applicable throughout the mine life cycle. it's providing real value to organisations because they're able to identify risk early and mitigate it before it becomes expensive. So you can see a whole raft of examples of where we've used it. Exploration, exploration is really useful for identifying where the water supply is going to come from. Is it going to be a major risk to the project, and what the alternatives are. You can also define appropriate baseline surveys and scope out any low impact aspects. We've also combined it with water chemistry to do an exploration tool. So you take the water chemistry and you know where the groundwater is coming from. This is groundwater chemistry. You know where the groundwater is coming from, and so therefore you've got an anomalous groundwater catchment. So we can use it in several ways in exploration stage. Like I said, at the PFS stage, I gave a couple of examples, proactively identifying what some of the surprises that you might be facing in the operational phase. Again, operational phase, looking at all of your current metrics, what's important, what you need to pay attention to in terms of regulators and so on. And then closure. You know, if you've been managing it well, managing water well, from exploration right through to closure, you're going to reduce your closure costs, reduce your closure surprises, and it's just going to make the closure a lot simpler and easier to defend. So, in conclusion, if water isn't currently on your mind as a project risk, it will have been in the past or it will be in the future. Even the best resource companies come across expensive surprises. So you need to start early to quantify your risk, get smarter in managing it, and safeguard your project value. Thank you.
Thanks very much, Joe. In my experience, water has been one of the trickiest parts to study, and I guess one of the bigger risk items for clients, which I'm sure a lot of you are aware of. So thanks very much for describing the whole process. The next presenter is, I met this chap last year, Mr. Russell Birrell. He's a principal geochemist for Globex Solutions. He's presenting on geochemical exploration for buried deposits, and he tells me he's been very busy the last year.
Thank you very much, Chris, and excuse me. Thank you, MINEX, for MINEX Europe, for the opportunity to speak today. I have to say, I've actually never presented in a sauna as big as this. I'm really impressed. So if I look like I'm about to faint over here, just bring beer, no water, that'll tip me into shock. So, okay, so let's move on. I'm going to talk about geochemistry very quickly and what has changed, particularly the last 3 or 4 years, but probably 10 years. In particular, how we can use geochemistry, the new geochemistry that's available now. Some of the game changers, believe it or not, is our understanding of nanoparticles, quantum physics, very important. Mineral systems, our understanding of big mineral systems or even small or medium-sized mineral systems has been really important in how we can interpret our geochemistry. The analytical technologies we have now are way in advance of what we've had in the past. We can get ultra-low detection limits for the periodic table almost, and we can get that at a commercial, in a commercial time frame, usually at a commercial cost. Some people may argue that that's not the case, but it is. But really, the really important things that have happened is the detection limits that we can now see routinely, and we can use those. I'm going to be talking about, I'll be presenting some information, and it's using ionic chemistry, geochemistry, something I've been involved with since the 1990s. But in particular, the last 3 years with the new ICPs and some of the development work that has gone in with the ALS laboratory in Loughrea in Ireland, that has really opened up a lot of areas for us. These are just some of the things that we can measure now, and in keeping with the theme of the conference, soil sampling, stream sampling is one of the lowest impact exploration technologies you can use. So, looking at the lithochemical associations, I won't dwell on this, but you can, whoops, sorry. Okay, here is just a copper moly porphyry. And as you can see, we can see these pathfinders not only beside these systems, but also over the top of them. So we can use that information very, very effectively. For example, moly, tungsten, tin, selenium, tellurium, bismuth, arsenic, antimony, lithium, thallium, as we move up a system. The real important thing that's happened is that we can now see those elements in soils that sit over the top of those particular systems. Now, how they release, how they get there, how the anomalies form, that's another topic. We certainly don't have time to talk about that today. But we can actually see those fingerprints of the footprints that sit down below. And this has really been the main game changer for us in the last 3 years. We now have a template, if you like, of the footprint, and we can start looking for those footprints in the surface soils. Why detection levels so low? Well, here's an example, a 3 million ounce deposit buried under about 40 metres of cover. In 1992, our detection level was low, 1 ppb. In 1993, that came down to about a half a ppb. 1997, it was about 0.25. And really, from about 2003, we've really had detection levels for gold at about 100 to 200 parts per trillion, really. Now, in some cases, laboratories are a little bit reluctant to give that, set those element standards, but the important thing is when you can see those levels, suddenly you can actually start to see the anomalies that sit over the top of deposits. And of course, the advantage now is since 2003, and particularly the last 3 to 4 years, we can almost see those sorts of levels for really critical pathfinders. Arsenic, antimony, bismuth, tellurium, indium, selenium, mercury, iodine, bromine, all these sort of elements are becoming very important. I'm going to show you some information from a project I've been working on. Diversified Asset Holdings is just a small private company. They have the Keel Deposit in Ireland. It's an Irish-based metal deposit. Interesting deposit that a company did some work, a few years ago now, and ended up sinking a shaft to 4 levels. Got down there with the view to start mining, and then suddenly realised they'd got the model wrong. It wasn't a SEDX type deposit, it wasn't flat lying, it was actually a shear controlled base metal deposit, and so the shaft is still sitting there and nothing has ever come out of it. So the company is, as I said, a small private company. They're developing it. They've probably got the resource up towards 10 million tonnes at the moment, and around about the same grade. So it's starting to get up there. So it's an interesting project. The photographs down the bottom here, just to give you an idea, it is covered. It's buried variably from about 10 metres to probably about 200 metres. As we move to the southwest, that'll become obvious in a moment. So that's the deposit. Again, quickly, 7 metres at 12.5 grams, percent zinc, 5 metres at 12.8. So it is high grade, but as I said, it's a shear control system. It's not your typical flat-lying sedimentary thing. This was a, oops, sorry, big fingers. I need to go back one more. Okay, so this was an orientation line over the main keel mineralisation. And over here, this is in the brown, this is just the zinc cadmium responses. In the green there is the lead antimony, and you can see that there is a response sitting over the keel, but there's also this response sitting out here, which was unknown. These other elements, and I guess this is hard for you to see, but the colours are, the blue is arsenic and antimony, and the yellowy colour over here is indium and thallium. This colour is silver and mercury. The green colour is iodine, bromine, rubidium, cesium, and so on. So basically all I'm saying is these things have multi-element signatures, but they don't necessarily all sit on top of each other, and that's really important for us. So this has picked up the mineralisation quite successfully. And then another line at the same time was done just to see what was happening along strike and to see if this trend, which hasn't been drilled, continued out here. This colour, I should have said, the image behind here is a gravity image. And this was the response. This colour here is the zinc cadmium, not so much lead antimony, but again we're getting arsenic antimony, indium thallium, and then silver mercury, iodine bromine, all sitting here, which is this position in here. So this was the orientation survey. Okay, to look at the geochemistry, this is what it looked like after we had done the work. And again, this is just zinc cadmium. This is the Keel Deposit up here. So from here on, it's about 20 plus metres, and it starts to get deeper as we move out down through here. This is rare earths. This is copper, and you notice it doesn't all sit together. Over here, lithium, interesting pattern. I'm not going to dwell on why these things are here. There are reasons for it. But I just wanted to point out that we see this zonation. The gold, the silver and the palladium is very interesting and completely unknown. This gold anomaly down here is also interesting. When I was presenting at this conference, there was a talk from a professor from Leeds University who's done a lot of work on nuggets, gold nuggets, and he said that in fact that's quite interesting because he had been able to identify palladium crystals within gold nuggets. Not at Keel, but certainly in Ireland. And so the palladium is probably making perfect sense. And again, I just put this up. This is moly, and this was the gold moly area we talked about. This is a trend coming through here. You'll notice there's bismuth, niobium, cobalt, and so on. Cobalt's an interesting one. Quite often cobalt is associated with pyrite. So these are the sort of patterns that we have been able to see. And just to try and summarise that really coarsely and very crudely, this is the zinc cadmium envelope, if you like. The copper, lead, rare earths sit somewhere like that. Down the bottom we have the gold, silver, palladium, but it also has mercury, arsenic, antimony in it. We have this feature sitting out here, which we really don't know what a lot of these things are yet. They haven't been drilled, they're unknown. But this is copper, moly, gold, silver, copper, moly, arsenic, antimony, and then we've got this feature running straight across through the whole thing. I should point out that we've worked on a number of these projects in Ireland, and these sort of patterns are not dissimilar. So we are seeing these multi-element patterns moving around these big systems and big deposits. How do you use that? For example, in this is a La Salle project in Venezuela, and if you look at the geochemistry here, and this is really very simple, it's just nickel, gold, silver, cobalt, palladium, nothing special, but you can interpret a lot from this geochemistry. For example, this is a lithological change. As it turns out, it's a shear-hosted thing. This is the gold response, this is the silver response. Primary gold usually has a silver response. It's a very good pathfinder, and in Ireland it looks like we also have palladium. I've seen that elsewhere, particularly in the Iberian Peninsula. This response out here was very, very high gold in lateritic soils and trenches, excuse me, but you'll notice there's very little silver involved here, so it's a hydromorphic. It's the infamous lateritic mushroom effect sitting out here. Very, very high grades of gold at the surface, and I think this was about 7 metres at 3 or 4 grams, or it may have been more than that, I can't remember. So how do we use this sort of approach? This is some of the work we've been doing in the Nordic regions, trying to unravel boulder trains or down ice positions. Excuse me. What we notice is that where we have a genuine target, we don't just get our commodity element responses. We can now start looking for the fingerprints, in other words, the signatures of the pathfinders that sit around the edge of the actual primary mineralisation. As you dismantle that and you move it away, and that can be a movement physically or you can move it chemically, as you move that away, this fingerprint starts to become dismembered. And yes, you can get very high values of commodity elements, there's no doubt about that. But the trick to using this technology is to look for these patterns as you move away. And if you can see this pattern, then you have a much better chance of drilling into something that's going to be worthwhile. Okay, so the new focus for geochemistry, we need to look for these processes as well as their signatures. We need to identify that primary signal and not just secondary effects. In other words, we need to look further than other processes at the surface which can form anomalies, which can often be false anomalies. They can be false positives or they can be false negatives. We can use our low level of detection to identify very subtle but nevertheless very real mineralogical signals, and we can also now start using isotopic levels, particularly lead isotopes, to try and pinpoint primary sources for the metal. What we have is a geochemical method that is trying to minimise the effect of near-surface processes. In other words, pre-concentration, either through biological or other sort of chemical effects. We're trying to see the signal before it gets processed by natural processes at the surface, and by doing that we can enhance its deep sensing capability. So what I would say about the geochemistry, first, it's usually a crazy idea. Again, my apologies. We have technological advances. Some of the ideas are not so crazy anymore. Certainly better technology comes along and we start to see things, or knowledge, not only technology but knowledge, and some of the doors start to open. And I think where we are now with geochemistry, surface geochemistry, is we're up in here. We really have some fantastic technology available routinely, and some of these doors are starting to open to us. Thank you very much.
Thanks very much.
Good afternoon, everyone. I've been asked to trim a few minutes off, so I'll do my very best. There's been a revolution taking place over the last 15 years, and many of you in the room have been involved in that revolution, and this talk will describe Olympus's role in that revolution over the last 10 years. The title is the Portable Xrf Decade, and it's an abbreviated version of a talk that my colleague Aaron Bench will be giving, a keynote talk will be giving next week in Vancouver at the RFG conference. But a small slide about Olympus. Yes, it is the Japanese camera company whose main core business is in medical equipment. But we also have an analytical instruments division which deal in portable X-ray fluorescence analyzers and portable X-ray diffraction systems. So that's X-ray diffraction, X-ray fluorescence, and we also are well known for our microscopes. And we're the only company that can combine those three technologies to give an integrated geoscience solution. So to go back and give you Physics 101, XRF is giving elemental chemistry. We have a handheld XRF on the Olympus stand over here, and if you're interested, we can show you how that works. You pull the trigger, you get a measurement of the chemistry of the sample, whether it's core, soil, rock, in 30 seconds. Arsenic, copper, lead, zinc, nickel, cobalt. That's what this technology does, and that's the core technology I'm going to talk about today. But we also have this portable X-ray diffraction system, which is like nothing you can find anywhere else. The technology is used on the Mars Curiosity rover, doing the mineralogy of Mars as we speak today. If you want more information about that, I can share that with you over the course of the next few days. But the inspiration for this talk comes from Paul Agnew at Rio Tinto Exploration, who gave a presentation
last year at Exploration 2017 in Toronto and coined the term the Portable Geochemistry Decade. This conference is only held once every 10 years, so Paul was asked to look at the trend of geochemistry in the last decade, and it really has been portable geochemistry, the ability to get results in the field next to the sample. And so you can read his paper, which is part of that. So the aim of the talk is to summarise the advancements over the last 10 years. Many of them you will know, but there may be some points that I discuss in the next 10 minutes that you haven't heard before. I think I bit off a little bit more than I could chew in suggesting the key aspects of developments over the last 10 years in terms of innovation of the analysers themselves, development of methods, quality control, data management and best practice workflow, developments in sample preparation and in the application of the technology. How is the instrument being used? So I'll very briefly summarise some of these 4 aspects of the last 10 years. So in terms of the hardware, software, the computing power of the technology and ruggedisation innovations, 2005 Innovex Systems, who were acquired by Olympus, released this model. It's called an Alpha. It had a silicon pin detector. It could only measure down to titanium, and you'll note the 200 electron volts and 12,000 counts per second. So that's how many counts per second the instrument could measure of any element, fluorescent X-ray coming back into it. So as we go through the iterations of the technology during this time, you'll see movement towards ruggedisation, increased computing power. This instrument's got the same detector resolution and counts per second as its forebear, but in 2010 the Delta was released. We used a different design detector, silicon drift detector, which means we could measure 50,000 counts per second, which means lower detection limits, shorter test times. We could measure down to magnesium on the periodic table, rare earth elements, and the computing power of this analyzer was about 10 times its original Alpha. The latest model instrument that we released in 2016 is called the Vanta. It's got a lower detector resolution, huge power in terms of computing capability and counts per second, and we're using Linux instead of Windows, and is a revolution in the Portable Xrf world. So the key features of this new instrument are ruggedisation, and the main ruggedisation features are it's IP rated against dust and water. You can genuinely operate it to 50 degrees C. Portable Xrfs have had a historical problem in hot climates. I'm not sure how they'd cope in this room today, but we've got a detector shutter. It's drop tested. We've done a lot of work on count rate and digital pulse processing. It's Wi-Fi connected, it's cloud enabled, it's got an embedded GPS, and it's a completely new redesign of the software to make it more intuitive. And there's not many XRFs in the world that you can say you can do this to. You can drop it and you can get it extremely wet. So one of the early innovations we looked at was putting cameras inside the nose of the instruments. We did this as early as 2010 so that we could collimate the X-ray beam and really look at small mineral inclusions within rocks for particular interest. In 2013, we tried to quantify the improvement in computing power and counts per second, and so some of the work we were doing with BHP in this in this slide shows that we could get the same performance on a 15-second test that we previously had to do over 90 seconds when doing some iron work, silica work. And I've got a lot more case studies and a lot more data if you're interested in knowing more. Now, XRFs are not ideal for gold analysis. Obviously, when you send your samples to the lab, they use fire assay. But there are areas where the instrument can work in quartz vein environments. And as early as 2013, in an interference-free matrix in silica-based samples, we were seeing 1 gram per tonne gold in certified reference materials in 30 seconds. So to cover the other features of the last 10 years, we've really focused on quality assurance and quality control. So a lot of the well-known suppliers of certified reference materials now supply portable XRF kits. You can get those kits made to your matrix. And QA/QC is one of the most important aspects of any portable XRF program. Testing certified reference materials that are matrix matched to your deposit, or samples that have been assayed from your deposit are even better. Early on we realised one of the key advantages of portable XRF is to generate a lot of data, but that can also be one of its big disadvantages, and that's managing that data. So one of the early things we did was ensure we could seamlessly integrate the data from our systems into the software systems that mineral explorers and miners were using. These are the ones we're currently aligned with, but watch this space for integration with a lot of different other packages towards the end of the year. And we've been writing about workflows and best practice application of this technology for a long time. The technology has a lot of strengths, but it also has a lot of weaknesses. And it's important that customers understand the weaknesses of this technology so that they can get value out of it. And it's not only us that have been writing about best practice applications of the technology, but it's our customers as well, such as GTK, the Geological Survey of Finland, who've got 15 of our handheld XRFs and write about their experiences and write about maximising the value of this technology. We formed partnerships very early on in our gestation with CSIRO and well-known companies to work on method development. And in 2014, there was a joint paper released by us and CSIRO in Australia that's really become the most cited reference for workflows and method development for portable XRF. And we've been working with a lot of partners to develop standard operating procedures using portable XRF. The Camiro project between 2010 and 2012 was a very important cornerstone moment for the technology because there was an absence of standards and general operating procedures. And so Camiro aimed to wrap some rules around using portable XRF. And this is an example of Goldfields testing a certified reference material over the period of 2 years to ensure they understood if there was any drift happening in their XRF. So, sample preparation. I was publishing as early as 2003 on the effects of sample preparation on XRF performance, and this was done in Tasmania at the Mount Lyell mine, showing the effects of pulps on partially prepared samples, crushed samples, on samples directly from the mine face. Portable XRF prefers homogeneous samples. You can get great results on partially prepared samples and for all sorts of samples, as long as you understand whatever you're placing in front of the instrument's window is what you want to measure. And this is some of the work that's gone on around sample preparation. How am I going? 2 minutes? Okay. to the point where we are today, where there's third-party companies such as Reflex who are now offering field portable sample preparation solutions specifically designed at portable XRF users. We've got mini dryers, mini crushers, mini grinders and mini presses so that you can get a homogeneous sample from a rock within minutes of collecting that sample. When I was sitting down here today thinking about this presentation, and I looked to the sponsors, so Olympus Portable XRF users include SRK Consulting, SRK Exploration, ERM, Central Asia Metals, Reservoir Minerals, Minico, Rakita, Tethian, and I believe Euromax are also using Portable XRF. It's not one of ours, unfortunately. But it's become ubiquitous, this technology, within the industry. And we're seeing that now with third-party companies producing accessories that support the technology. So I'll briefly go through some of the innovative applications I outlined in the abstract. And I thought I'll start with the implications for this technology within JORC and 43101 reporting, because I thought that would probably be the most controversial and therefore the most interesting subject matter. But I really like to show this front slide, which was the cover slide of a presentation given at a Portable XRF workshop in Toronto, PDAC, in 2016, I think, which really says it all. It says where we are today with, you know, some of the most reputable consultants in the world supporting this technology. But as early as 2010, AMC consultants were advising companies on how they should cope with handheld XRF and reporting in line with the JORC code. But the big development was in 2012 when handheld XRF, in the new JORC 2012, when handheld XRF was specifically mentioned in Table 1 on how you should report your handheld XRF data if you intend to make public announcements. So that was a real coming of age for the technology as well. And where we then start to get other consultants advising the industry on how to report portable XRF data in accordance with the codes. Early adopters included Newmont, not measuring gold, but measuring arsenic, antimony, copper, lead, zinc as pathfinders. Barrick were doing geomet surveys as early as 2009. And to finish with the other applications, which I thought might be interesting, my background is an environmental scientist. I discovered portable XRF cleaning up contaminated sites. So it's fascinating to see that this technology started in environmental. We've now introduced it into mineral exploration, mining, mineral processing, and the environmental applications of the mining industry. So for me, having started with this technology in 2000, it's been a fantastic journey and very fulfilling last 18 years, to be honest, but I'm digressing. Other applications include gold in bullion, gold in activated carbon. We've done a lot of work on light rare earths. We cannot measure lithium, but we measure rubidium-potassium ratios, which are very indicative pegmatites. Done a lot of work on cobalt lately, of course, with battery metals. And Goldfields were one of the first companies to really innovate with this technology and do rock typing, lithogeochemistry, titanium over chromium, aluminium over titanium ratios of the immobile elements. First Quantum were doing work as early as 2011 on blast holes, doing grade control. And the moment where we knew the technology had been accepted, I loved your slide, Russell, about how technology starts out being defended and then accepted in the end. You can now go to ALS and ask them to analyse your samples with an Olympus Portable XRF instrument. So we really have, the technology really has come of age. So our keys have been engaging with the industry, publishing, doing case studies, having a dedicated mining team, and respecting the fundamentals around sampling, homogeneity, X-ray physics, and quality control and quality assurance. So we've invested in our products, and I'll hand over to the next speaker. Thank you.
You've answered a few questions I had on XRF over the years. So, and it really has gone a long way. So, next speaker we have here is Professor
The same.
from
Hello, everybody. I think people are tired, so we have to be short. I'll try to be very short in my presentation. I'm going to talk about direction drilling and whole path control. Today a lot of presentation about exploration. Actually, the geologists, they need correct information. The mining companies, they demand also correct information from the exploration. And what we do, we help geologists to get it. How? Just by steering the borehole in order to get the core or the information from the place in the ore body they want to get it. Our company, BG Drilling Solutions, Bulgarian company, who are very small compared to the many of the companies which were presented here in this forum. So we developed our own technology and provide services all over the globe. Somebody in the lunch asked me, how did you manage? How you get successful in the market? So we have a couple of secrets. The first one is the team. Our team is university-educated engineers. Drilling is simple, but it needs a lot of knowledge, and actually through the years we gain a lot of experience about the drilling, so we know how to do it. And then we have R&D team, which develops the tools. We are testing our tool. We are proving that it's reliable, robust, so we can provide the quality services for our clients. Actually, in this slide, you can see how the team was expanding the last couple of years. The next key to the success was actually the field we were drilling. Directional drilling is well known in the oil business, but in mineral exploration, it has old tradition. It's not so popular and spread it all over the globe. So we gain experience through our projects, starting in Brazil, in Hong Kong, in Singapore, in South Korea, being partners with our companies. And this is one of the reasons for our success. Lately, we realized that the most of the geology exploration companies, they know about directional drilling, but they don't know how to apply it. So we launched the whole path control as a new services. We are trying to help the geologists to control the borehole trajectory during drilling. We call it the war room. So we provide 24 hours services, having real-time information, and then we can advise the drilling company how to drill, even without using directional drilling. A couple of words about our technology. We use the so-called continuous wedging tool. Unlike the other tools available in the market, our tool is mechanical operated. Unlike the core barrels, for instance, Livingstones and David Drill, they're hydraulically operated. The bottom hole motors, they are also hydraulically operated tools. So our tool being mechanically operated, it doesn't have restriction with respect to the depth. So we can drill and steer the borehole to depth up to 2,000 and more than 2,000 meters. Some of the data you can see over there. We have N-size and B-size tools. We can deviate the boreholes with a Doppler severity from 0.2 to 1.5 degrees per meter. We can drill almost in all geotechnical conditions except broken formations, if they are loose also. So this is a big advantage of our technology. Our clients, Vale, Glencore, AngloGold, Shanti, Yamana Gold, Trevali, Hudbay Minerals. At the moment we work in Canada, in Sudbury region. We started those days with the mini diamond in Canada too. We work in Peru at the moment with Trevali Mining. So this is a list of companies we work and we have been working with. And at the end of my presentation, I'm going to present you one of our projects. It was actually Vale's Copper Cliff South Mine in Sudbury. It was closed for a couple of years, so they decided to reopen the shafts. And in order to do this, they need to seal the existing shaft. So we had to drill a couple of boreholes around the shaft in order to squeeze cement and seal the shaft. And what we did drill boreholes strictly vertical. For all the boreholes, we used 45 days. The drilling program metric was 2,200 meters. To control the boreholes, 130 gyro surveys were done. We made a 20 intervention with our tool and 20 gyro orientation. So this slide gives a little bit more detailed information about the steering. We made 1, 2, 3 correction in order to get the borehole in a safety envelope within 3 foot. This is the border of the borehole. So this is one good example how our technology can be applied in the real life. So that's all. If you have questions, please welcome to our booth so we can talk about our technology.
Thank you very much, Dr. Dumont. And you can see some technologies that are being developed in the Balkans, being heading all over the world, being used. Next presenter is Ralph Lopera. He's Director of Sales and Business Development for Sidra Mineral Processing. I think you've probably seen his devices up the back there, but he's presented assessing the benefits of automatic grinding control using PST technologies for true online particle size measurement. Thank you.
Thanks, Chris. Dobra, good afternoon. First of all, a thank you to all of you that you stay with us under these circumstances, and a special thank to the translators in this small Finnish sauna. Okay, it's a pleasure to introduce a unique, new patented technology to you called particle size measurement, PST. And if you are interested in the next days, you can come visit me at the booth and I will introduce the technology to you. And I would like to give you one good reason why you still should listen to me, because we are talking about net profit. That's the reason that we are all here, net profit in minerals processing, and that's exactly what we are looking for. Sidra is a process optimization company, so we look into mineral processing companies and we help them to improve the processes. Okay. Next slide. Doesn't work. Okay. So if we talk about minerals processing, what is the major challenging all minerals processing companies have in the world? First of all, the ore grade is the ore grade. You can't change the ore grade. So if you have a deposit and you have the deposit under your control, you can't change the ore grade. The end price of the finished product is a world market price. So if you want to create net profit, you have to work in between. So if you can improve your throughput, if you can improve your recovery rate, so the net metal production will increase. That's exactly where your profit is. So you need technologies and methodology to exactly do that. So if you look into particle size measurement, it's really interesting if you look into our industry. Most of the company are still using sieving kits to understand the particle size. So you take samples, sieve them, and get later on a result of your laboratory. That's in the digital world of 2018, state of the art. In the most modern ones, you get particle size analyzers. Companies like Autotech, Thermo Scientific, Fisher offer this type of technologies. But this is still sampling. You take samples and you get a full stream analysis of your complete production. Our technology is totally different. We installed a probe on the overflow of the hydrocyclones, and you get real time your particle size. Okay, let's have a look into how that looks like. Here you can see the installed probes on your hydrocyclone. Depending on the size of batteries, each single cyclone will be monitored. And as engineers, we all learned the closed control loop. What you can measure, you can manage. How does it work? The basic technology behind that is sonar. So it's an acoustic system. We measure the impact of the particles at the probe. How is it calibrated? It's only once calibrated when it's installed. So if you later on have to reinstall the probe, you don't have to recalibrate it again. So it's just one time in the early stage where we want to understand how your micron, your P80 looks like. So the calibration is done very easily. You take samples from the production and you take also the measurement of the PST system and you compare them. And based on the coloration, you get a clear calibration. So if you want to think about why should I invest on such a system, I think the most important question is the return on investment. So if I invest money into that, what can it bring to me? So, and that's again coming back to the net metal production. So the return on investment of such a system is below 6 months. Those people which are maybe managing assets or are in the financial department of assets will understand that 6 months is a very, very short payback time of such a system. So the increase of your net metal production is around 3%. Everybody here can easily calculate what 3% more net metal production means for you in profit. Okay. How that can be calculated. So if you want to know exactly for your company, what is the return on investment? So it's very simple. You can put your own data. Doesn't matter if you are copper, gold, or in other minerals. So you take the ore throughput rate, tons per hour, the ground production reference size in microns, total copper heat rate, total copper recovery, which will bring you to the calculation of the net metal production. For sure, you have also to think about the data, and you have to filter the data, right? Because there is a paradoxon, and I don't know if there are any metallurgists here. Metallurgists learn very easily and hardly that there's a paradoxon in this industry. If you want to increase your throughput in tons, you pay normally a price on the recovery rate. And that is based on the fines, the coarse material. So if you can measure your production, you can move your production into the comfort zone, right? Into the exact best size for your production. And that's exactly what these systems bring. And that is an automated system, so it's not based on worker control. So it is connected to your DCS automation system, and your production will be controlled automatically. It's because if you work with worker control, you know that you have a human error factor. Even if you have different shifts, you will see different production rates, right? So this system will offer you that you can increase your throughput by staying with your recovery rate or even improve your recovery rate. Okay, I will finish now because it was a long day for all of us, and I will be more than happy to share information about the systems and what does that bring to you. Could be tonight or even later on the next days on the booth. Thank you very much.